Today we begin the first in a series of lectures about eigenvalues and eigenvectors. First, let's review some concepts from the previous lesson. Let's say that A is an n by n square matrix. We'd like to consider B various matrices obtained from A by performing an elementary operation. Let's say that B is that matrix obtained from A by interchanging two rows. Then the determinant of B is negative the determinant of A. Similarly, let's say that B is obtained from A by multiplying a row of A by a scalar k. Then the determinant of B is k times the determinant of A. And finally, say that B is obtained from A by adding a multiple of one row to another. Then the determinant of B equals the determinant of A. If A is any n by n matrix, and B is any other n by n matrix, then the determinant of A times B is the determinant of A times the determinant of B. A is invertible if and only if its determinant is non-zero. In particular, the determinant of the inverse of A is the reciprocal of the determinant. And finally, the determinant of the transpose of A is the same as the determinant of A. In the last lesson, we presented a very important idea on how to find the solution to a system of equations. This is what we called Cramer's rule. Say that we have a system of n equations and n unknowns. These unknowns being the variables x1, x2 through x sub n. We can write this as a single equation in the form a times x equals b for some n by n matrix A. Let's assume for the moment that the determinant of A is non-zero. Then we know that A is invertible, and in fact, the inverse of A is the classical adjoint divided by the determinant of A. Remember that the classical adjoint is the transpose of the cofactor matrix. Our system then has a unique solution given by the inverse of A times the vector on the right-hand side, the vector B. We can write this more simply by saying, let's consider the solution by looking at each individual variable x sub k. We can express x sub k as the ratio of two determinants. It's the determinant of m sub k divided by the determinant of A, where n sub k is that n by n matrix obtained from A by replacing the kth column with the vector on the right-hand side, B. We give a couple of examples. Say that we have a system of two equations and two unknowns, and let's assume that our determinant is non-zero. Then Cramer's rule says that we can express the solution, the variables x and y, as the ratio of two determinants, where the variable x corresponds to that matrix, where we replace the first column with b1, b2, and the variable y corresponds to replacing the second column with b1, b2. Now let's say that we have a system of three equations and three unknowns. Again, let's assume that our determinant is non-zero. Then Cramer's rule asserts that we can express the solution, that is the variables x, y, and z, also by the ratio of two determinants. For the variable x, we replace in the first column with b1, b2, b3. For the variable y, we replace in the second column with b1, b2, b3. And for the variable z, we'll replace in the third column with b1, b2, b3. We also would like to review some concepts of linear transformations and their matrix representations, since we'll be discussing some applications for the next few lessons. Let's say that V and W are two vector spaces. Recall that a map T has a domain V and a codomain W. Once we have such a mapping T, the following statements are equivalent. That is, T preserves vector addition and preserves scalar multiplication, or for any linear combination, then T will map that to another linear combination. Any well-defined map satisfying either of these is said to be a linear transformation. Let's say that V is a vector space and we have a basis beta. Well, the concept of a basis is that the following two statements are equivalent for any given subset. First, this subset spans V, and that this subset is a linearly independent set. And second, every vector x can be expressed as a unique linear combination of vectors from this set beta. We'll define a basis by using this concept here. That is, any subset satisfying either of these two equivalent statements. We're going to be concerned very specifically with an ordered basis. That is, we really do care about the order in which we write these down. For any vector x, we know that we can express it as a unique linear combination. That is a linear combination where the scalars a1, a2 through a sub n are uniquely determined. So we'll use this to define the coordinate vector of a vector x. The idea is that we take a vector x from our vector space V, and relative to this ordered basis beta, we can then write down an n-dimensional vector that just keeps track of the scalars a1, a2 through a sub n. More generally, let's say that V and W are two vector spaces, and we have bases beta for V and gamma for W. Then the map that takes x to its coordinate vector is a linear transformation. And in fact, even better, when T is a linear transformation from V to W, then there is a matrix A that makes the diagram you see here on your screen commute. This phi sub beta is called the standard representation of the vector space V with respect to beta, and this matrix A is called the matrix representation of T in the ordered bases beta and gamma. For what we're going to say for the next few lessons, we will only focus on the case when V equals W. That is, when the codomain equals the domain. Simply put, why are we defining these standard representation and matrix representation matrices? Well, remember that given a vector x, we have a unique linear combination in terms of the elements of the basis beta. We really only need to keep track of the scalars a1, a2 through a sub n. That's the concept of a standard representation. Just keep track of these scalars. More generally, say that we have a linear transformation T. Again, we can express the image of each of the basis elements v sub I from beta as a linear combination of the basis elements w sub j from gamma. But we really only need to keep track of these scalars a sub ij. Recall from the way we've set this up, if you take a look at the image tv1, then here we have an a11 times w1 plus an a21 times w2 plus an am1 times wm. Those scalars get placed in the first column of our matrix representation A, a11, a21 through am1. Again, they are placed in the first column of A. To kind of explain the properties that we have here, let's say that V, W, and Z are three vector spaces. We'll denote script L of VW as the collection of linear transformations T from V to W. Then the set script VW is a vector space. Second, say that T and U are two linear transformations. T maps from V to W, and U maps from W to Z. Then the composition U circle T mapping from V to Z is also a linear transformation. Finally, let's say that V has a basis beta, W has a basis gamma, and Z has a basis alpha. Then we can consider the matrix representation of the composition U circle T going from basis beta to alpha as the product of the matrix representations of U going from gamma to alpha times the matrix representation of T going from beta to gamma. It may be useful to keep the following diagram in mind. You'll see that on the left we have maps from V to W to Z. Inside of those vector spaces, up above, we have our bases beta, gamma, and alpha. And down below, we have our standard representations phi sub beta, phi sub gamma, and phi sub alpha. All of these will correspond to the various matrices A and B, and you'll see at the bottom we actually do have a new matrix B times A. But now, by looking at the various arrows in the compositions, we see that we really do have the product of matrices. Today we'd like to discuss eigenvalues and eigenvectors. So let's start with some definitions. We'll say that a linear transformation T is diagonalizable if there exists an ordered basis beta such that the matrix representation from beta to beta is a diagonal matrix. Notice that this is the same thing as saying that for all of the elements v sub j in the basis beta, T of v sub j is some scalar lambda j times v sub j. This is equivalent to saying that our matrix representation is a diagonal matrix. A square matrix A is said to be diagonalizable if the linear transformation left multiplication by A is also diagonalizable. To be more precise, let's say that gamma is the standard basis for f to the n. Then we know that our matrix A is just a matrix representation of left multiplication by A with respect to the standard basis. For any other basis, beta, then we know that we can have a change of coordinate matrix Q going between the two bases, beta and gamma. This means that the matrix product Q inverse times A times Q is the matrix representation for L of A going from beta to beta. We like to have a basis beta such that this product Q inverse AQ is a diagonal matrix. You'll notice that the word diagonalizable really means able to be made diagonal. That's essentially what we're doing here, trying to find a basis beta either for the linear transformation T or for the matrix A such that we can make a matrix diagonal. We'll continue with a couple more definitions here. Again, say that T is a linear transformation from a vector space V to itself. A non-zero vector lowercase v is said to be an eigenvector for the linear transformation T if there exists a scalar lambda such that T of lowercase v is lambda times lowercase v. Please recall here that we want our vector lowercase v to be a non-zero vector. The scalar lambda is called the eigenvalue associated to the eigenvector lowercase v. Similarly, say that A is an n by n matrix. A vector x is said to be an eigenvector for our matrix A if there exists a scalar lambda such that A times x is lambda times x. The scalar lambda is similarly called the eigenvalue associated to the eigenvector x. For the next few lectures, we're going to be concerned with how to compute eigenvectors and how to compute eigenvalues, either for linear transformations T or for matrices A. To this end, we really have the following diagonalization problem. First, given a linear transformation T going from a vector space V to itself, does there exist an ordered basis beta such that the matrix representation from beta to beta is a diagonal matrix? Second, if such a basis beta exists, how can it be found? Again, we're going to focus on these two questions over the next several lessons. Before we go any further, let's try to present a motivating example to explain how we might find such a basis beta. Let's consider the real plane V equals R2. We'll fix a number m, and let's consider the linear transformation that you see here on your screen. Simply put, this is a reflection about a line defined by y equals mx. For example, when m is equal to 0, this linear transformation takes a vector x comma y to x comma negative y. This means that this is the reflection about the x-axis, namely the line y is equal to 0. In general, you can see from the diagram here what's happening. We have the line that you see in the middle of the screen, which will be, for example, y equals mx. You then have this object in the middle of the screen, which may be, let's say, a quadrilateral, a four-sided figure. We can then reflect this four-sided figure over the line y equals mx to find the quadrilateral figure that's now below the line y equals mx. This is an example of what this linear transformation T would do. It would take an object, maybe a set of points x comma y, and it would reflect it over this line y equals mx. Let's give a slightly simpler way to view this transformation. Recall the following. Let's say that A and B are two real numbers, not both 0, and we'll denote the two vectors u sub 1 and u sub 2 that you see on your screen. We found earlier in the semester that this set of vectors forms a basis for R2. For example, we can recover the standard basis E1, E2 by setting A is equal to 1 and B is equal to 0, but we're going to focus on our basis beta in terms of the vectors v1 and v2 by setting A is equal to 1 and B is equal to m. We define this so that the span of u1 is just the line y equals mx. That is, v1 tells us the direction of the line y equals mx. However, the span of v2 is actually the line y equals negative 1 over mx, which is just the line perpendicular to L. We actually saw all of this before on our previous homework set. In particular, let's take t and let's apply it to these vectors e1, e2, v1, and v2. If we take the standard basis vectors e1 and e2, t sends these to the two vectors that you see on the upper left-hand part of your screen. On the other hand, if we take t and apply it to the new vectors, remember that v1 tells us the direction of the line L, and v2 tells us the direction of the perpendicular line L perp. T of v1 is positive v1. This should make sense because if we're reflecting over the line L, then it really shouldn't do anything to the line L itself. However, for v2, t of v2 is negative v2. Again, this should make sense because if we have a direction pointing above in the perpendicular direction, t will send that now pointing below in the negative of the perpendicular to v direction. But now we can compute the various matrices as the standard representations. Recall that if we wanted to compute our matrix A, then here, with respect to the standard basis, the matrix representation of T would just correspond to placing T of E1 in the first column and T of E2 in the second column. Again, this is how we can compute our matrix A. Now let's say that we wanted to compute the change of basis matrix, the change of coordinate matrix Q. Well, since gamma is the standard basis, this change of coordinate matrix corresponds to placing V1 in the first column of Q, and then placing V2 in the second column of Q. Finally, we can compute the product Q inverse AQ, which of course is just the matrix representation going from beta to beta. Here, we just have to take a look at what happens when we transform T of V1 to V1 and T of V2 to negative V2. Well, this of course corresponds to a diagonal matrix where the plus 1 in the upper left corresponds to the fact that T of V1 is positive V1, and the minus 1 in the lower right corresponds to the fact that T of V2 is negative V2. Again, geometrically, T leaves the line L alone, but it sends each point on the perpendicular line to its negative. That's the concept of a reflection through a line. It leaves every point on the line alone, but because we're reflecting, everything above L on the line L perp now goes to its negative. In particular, you'll see that with the way we've set up all of this, both T and the matrix A are diagonalizable. And in fact, Q inverse AQ is our desired diagonal matrix. We'll discuss all of this further in a previous lesson, but for now, thanks for watching.